Okay, so let's start. So welcome everybody to the webinar of today. The speaker of today is Alexander Oron, and his talk will be about buoyancy instability in a liquid layer subjected to an oblique temperature gradient. So as usual, I introduce the speaker very shortly, and then I leave him the stage. So after his PhD at Technion in 1987, Alexander Oron moved to Caltech, USA for a first postdoc between 1987 and 1988, followed by a second postdoc in the Center of Nonlinear Studies at Los Alamos, USA. Since 1990, he's professor at the Department of Mechanical Engineering at Technion in Israel, and he's member of the editorial board of Acta Mechanica and member of the editorial board of the advisory board of conference series like IMA, International Marangoni Association, and BFD, Bifurcation and Instability in Fluid Dynamics. His research interests are hydrodynamic instabilities, instabilities of thin liquid films, nonlinear evolution equations, fluid mechanics of in a low gravity and microgravity environment, free boundary problem in hydrodynamics, and numerical simulations of nonlinear phenomena in hydrodynamics. So it's with great pleasure that I introduce and I leave the floor to Alexander Oron for the presentation of for the talk of today. So Alex, I stopped sharing my screen, and you can start sharing yours.
Thank you very much, Francesco. Thank you very much for the introduction. Thank you very much for inviting me to give a talk. It's a great pleasure for me. Actually, wait, where is my, I think it's here. Now let me see if it will be possible. Wait, what happens here? No, something doesn't work well. Sorry for that. Stop sharing. Where is my presentation? It disappeared for some reason. Oops. Sorry, it disappeared. It was here on the screen, but
maybe you have it still in full screen mode, and maybe you Alt Tab, you can switch to it.
Yeah, it could be, but maybe just it's better just to go again to open it from the beginning, from the very beginning. Let's see, it's opening up. Sorry for complications.
Oh, don't worry.
It's kind of technological instability. It's something to think about. Wait, it says it's open, but I don't see it open. Oh, it's minimized for some reason. Oh, okay. Now it's on. Okay, so now let me share screen. Finally, I got it. This one. Share.
I think that's, yes, we see your presentation full screen.
Yeah, okay, thank you very much. Now let me activate the pointer. Okay, great. So thank you very much again. So my talk is about buoyancy instability in a liquid layer subjected to an oblique temperature gradient. And this work was done with my former postdoc, Dr. Prandtl, who just a few months ago accepted a position, a faculty position at the prestigious Chemical Engineering Department of IIT in Hyderabad in India. So the contents of my talk are very simple. After some introduction, I will talk about linear stability analysis in 3 dimensions for this problem, and which I will introduce shortly. And then time permitting, well, I hope time permits, I will go on with short account for weakly nonlinear analysis in actually 2 dimensions. Well, it sounds quite intriguing, but the emergence of an oblique temperature gradient seems to be quite widespread in many different technological phenomena or technological processes and other natural phenomena. For example, it seems to be quite relevant for 3D printing when a small volume of liquid is deposited either as a drop or a layer of liquid is deposited onto a surface or onto a substrate underneath, and this substrate may be either a solid or a mushy layer or another liquid or a combination of all of them. But again, the substrate doesn't have to have a planar horizontal shape. And in this case, in many cases, it's curved. And in this case, even if you activate the laser heating from above, just in an attempt to solidify the liquid, so due to the configuration, the temperature gradient may be oblique and not strictly vertical. Another thing is a jacketed chemical reactor, which consists of a chemical reactor. This is a vessel with all this stuff you want to cook there. And it's embedded into a hollow system of pipes, or maybe just one circular vessel in which the chemical reactor is embedded. So through this enclosure, you may circulate hot or cold water, basically along with the guidelines of the process you want to run, or you can circulate the water just on one side and not all around. So in this case, especially due to the fact that the hot water may be just on one side, and this fact may be combined with also with a non-planar shape of the bottom of the vessel. So here is the liquid. So again, the temperature gradient may be oblique. And even you can buy something like this in AliExpress, and even you can get a discount for it. So it's quite widespread equipment for chemical labs. Okay, so for those who are not really into this business, so let me very briefly introduce buoyancy instability. So imagine we have two differentially heated horizontal solid walls. One is here and one is here. This one is at higher temperature than the upper one, and gravity is acting in this direction. Now, imagine we take a liquid parcel just at some location, which is just at equilibrium due to the balance between its weight and the buoyancy force. But now let's displace it a little bit above its present location. So then the weight remains the same, but since the temperature decreases in the upward direction, and since normally the liquid density is a decreasing function of temperature, so then the buoyancy force in this case becomes larger than the weight, the original weight, so the particle will move upward and will not come back to its original position. The same argument may be made about the particle which is displaced down, and then the buoyancy force will become smaller than its weight, and then the particle will sink and will not come back to its original position. So it means that this physical configuration actually contains ingredients of instability due to just a very small disturbance. And actually, of course, it's a matter of whether the dissipative effects like viscosity of the liquid or its thermal diffusivity, whether they can stop this instability and return the particle back. The same thing may happen also in the case when we have two vertical walls, again differentially heated. This one is hot one and this one is cold one. Now imagine again we have a parcel in equilibrium. Now let's move it a little to the right, and now to the right of it the temperature at equilibrium is lower than here than its original position. So the density becomes larger and the weight now is smaller than the new buoyancy force. So the particle will move up. And in the gravity field again acting downward, and here near this wall, if you move a particle to the left, again the particle will get a smaller buoyancy force. So the weight of the particle, the original weight of the particle, will take this particle down. Again, the ingredients of buoyancy instability. Okay, so in our work, we'll consider this, basically this configuration with horizontal surfaces. Now, I will not go in details through previous literature, just saying that there are several configurations to be considered. One is when we have, one has a purely vertical temperature gradient, and this goes back to Benard 1900 and Rayleigh 1916 and so on and so on. Very popular, I would say, paradigmatic problem. Buoyancy instability can be also activated by purely horizontal temperature gradient. Like in the geophysical context, it's Hadley circulation, just a circulation of air between the equator and the tropic lines. And also buoyancy instability can be activated by an oblique temperature gradient. Here, number of works is much lower than in the other cases. There were still a few papers just recently in the last decade, but in the case of an oblique temperature gradient, only rigid boundaries or free configurations with an imposed temperature at both boundaries were considered. Now, in many of technological applications and natural settings, since the substrate is not a good conductor, so temperature cannot be imposed, and normally the liquid layer is exposed not to another solid surface, but rather to the atmosphere. So this was not considered, and we wanted to fill this gap. Okay, so this is a basic sketch of the problem I will consider. So we have a three-dimensional liquid layer, actually three-dimensional system, which consists of a poorly conducting substrate underneath, and this is a solid wall. There is a layer of a thickness d, and with the gravity going in this direction, and there is an interface between the liquid and gas, and the whole system is subjected to an oblique temperature gradient, which has, when I say the entire system, it means the wall underneath, the liquid layer, and the gas layer here above. The whole thing is subjected to an oblique temperature gradient, and this guy has two components. One component is what we call VTG, it's vertical temperature gradient. That's one of the vertical component of the oblique temperature gradient, and we call it minus beta. So minus means that the hot temperature is underneath. But there is another component of the temperature gradient, HTG, it's horizontal temperature gradient, and we denote it by minus eta star, and this means that the colder temperature are to the right and the hotter temperatures are to the left. Now the whole thing is of a large horizontal extent, L, which is assumed to be much larger than D. This will be particularly important in the nonlinear analysis. But since we scale the length in this problem with D, so the boundaries will appear as y equals 0 here and y equal 1 at the interface. So there is a bunch of liquid properties here, like reference density, like viscosity, like kinematic viscosity of the liquid, like thermal diffusivity and thermal conductivity of the liquid. And there is one more, since we consider the buoyancy instability, it's a volumetric expansion coefficient, which makes a difference. it's one of the main players here. Finally, we'll assume the interface to be free and non-deformable. Free in the sense that no a priori stresses are applied, just the interface, which is assumed to be non-deformable. There is a reason why not to deform it, but it's non-deformable. Just separating between the liquid phase and the gas phase. Okay, so just a little bit of equations and boundary conditions. The equations are standard, just continuity equation, Buoyancy approximation for the Navier-Stokes equations, and the heat conduction advection equation. The boundary conditions are the bottom no slip, no penetration, and imposed temperature gradient at the bottom is scaled such a way that -1 appears here. And at the interface, we have 0 vertical velocity component, free, 0 actually shear stresses, and the heat transfer condition at the free surface, at the interface. There are four dimensionless parameters here of the problem: the Prandtl number and the Rayleigh number, which is the main thing here, the Biot number, and this is eta, which is a relative strength of the HTG with respect to VTG. It will be also a very important parameter here. Now, beta, which is the value of the imposed VTG, it can be shown, at least in the base state, to be given by this expression, which includes the main thickness of the layer, the Biot number, and delta T, which is temperature difference across the layer along a vertical line. Since the whole thing is embedded into a horizontal temperature gradient, so the temperature of the bottom and the temperature of the liquid layer, so we'll see at least in its base state and in the gas phase, they are all varying with x linearly. So it's very important in which direction you measure your temperature difference here. Okay, so just this model has a few constraints. The first one, since we apply the Buoyancy approximation, and it's valid if alpha delta T is much smaller than 1, and this is equivalent to the requirement that the Rayleigh number should be much smaller than the Galileo number given here. And this is in turn is equivalent to the fact that the mean thickness of the layer should be larger than this value. Since we consider here Rayleigh numbers up to 10 to 9th, so in this case, at least for a water layer, the requirement says the D should be larger than 2 centimeters. The second requirement is, since we neglect the Marangoni effect here, actually Marangoni effect could have been included here quite easily, but for some reason I will tell you maybe later, we decided just to look at the pure effect of buoyancy and not combined with Marangoni. So this requires that the Rayleigh number should be much larger than the Marangoni number, which is defined here. Now, gamma is a negative temperature gradient of surface tension, which is normally positive for most liquids, apart of liquid metals, maybe. And this in turn is equivalent to D much larger than this value, D2. In case of water layer, it's 1 centimeter. So in summary, we will need to require that the mean thickness of the layer is larger than 2 centimeters for a water layer. Okay, so we look for the base state. So we assume that the base state has the following components. So in the x direction, which is the longitudinal direction, it should be a function of y. The two other fluid flow velocity component will be 0, and the pressure is a temperature as they should be obtained from the equations. Now, please note that the bar notation is just for the base state. Okay, so in this case, the set of equations reduces tremendously, so we need to solve this problem to find the base state. Now, since we have a problem of order 5, but there are, Yeah. So we need one more. I'm not saying that it's boundary condition, some integral conditions. So we assume that there is a return flow, and in this case, the total flow rate in the x direction across the layer should be 0. Okay, and it's easily found that the velocity is given in this case by this expression, just a cubic polynomial, and this velocity distribution has the following features. So for small y, just near the border, the solid wall underneath, it behaves like proportional to minus y, so which means it goes to the left. At y equals 0, it's equal to this value, so it goes to the right. Of course, somewhere at this location, y equal to 15 minus square root of 33 divided by 16, it vanishes. It will be also of importance down the road. So this is the velocity field. Now the temperature at the base state is found to be expressed in this form, which has several components. So the first component is a constant. It's not really important one. It varies linearly with eta, with x, actually going up to the left. And in the y direction, it has two components. One component is this linear guy, and this linear component exactly is due to the imposed vertical component of the temperature gradient, but it has another component, this one, which is given by a quintic polynomial. And this quintic polynomial, the whole thing, first, it's proportional to eta squared, so it doesn't have any importance which way the temperature gradient goes, to the left and to the right. And it turns out that this guy is always positive in the interval between 0 and 1. So this is what we call an induced VTG, and this induced VTG, since it's always positive, so it supplies sort of a resistance to the negative vertical imposed temperature gradient, so it may hinder the instability, and we'll see how it goes. And then the pressure, whatever it is, okay? So now I just to get a feeling what the temperature profile looks like, so I drew this sketch here. So this is y-axis, so it goes from 0 to 1, and this is the temperature, the full temperature given by these two terms. Okay, so in the case this coefficient is 0, so it's just linear, like in the case of imposed vertical temperature gradient, so it just monotonically decreases from y equals 0 to y equal 1. When this guy, the coefficient is not too big, like 1, so the temperature decreases first, but then it goes up, and it's quite not fully monotonic, but it's monotonic up to very near location to the upper surface, and then it decreases a little bit. If this coefficient gets larger, like 5, so then it has the same behavior and the same location of the maximum, just slightly underneath the interface, but essentially here near the wall, the bottom or the floor of the system, all of them behave quite similar. Okay, so linear stability analysis. So we superimpose small or infinitesimal disturbances on top of the base state. So the base state is bar, and this tilde value is just complex amplitude, and this is a normal form analysis. Now omega is a complex frequency, k is the wave number of the disturbance in the x direction, which we call streamwise disturbance wave number, and m is span-wise wave number. So just for the notation, so this omega complex frequency, it has two components. One is omega r, is a real part, and the imaginary part. So the real part is a frequency, if it's larger than 0, so it goes to the right, and if it's negative, it goes to the left. So the growth rate, if it's larger than 0, so then there is instability due to perturbation growth, and if it's negative, so the perturbation decay. Okay, so this is how this eigenvalue problem to be solved look like. D is a differentiation operator with respect to y. All of this tilde variables to be determined. Now, this eigenvalue problem needs to be solved numerically. You cannot solve it analytically. For omega as a function of two wave numbers, the streamwise and the spanwise, and the parameters, the Prandtl number, the Biot number, the Rayleigh number, and eta. Now, if you look carefully at the problem, you don't see eta. So eta is sort of hidden in the profiles of the base state in the V bar X and the T bar. So when you solve the problem, okay, so let me begin with the streamwise modes only. So for m equal to 0, let me first start with a case of Prandtl number larger than 0. So the leading eigenvalue of the spectrum you find looks like this. So this is the plane spanned by the frequency and the growth rate. So for example, for the case of eta equal to 0, which means that you have only a vertical temperature gradient, so you have the leading eigenvalue for this parameter set with a Rayleigh number of 400 and the Prandtl number 10, very small Biot number. So the leading eigenvalue is slightly positive with the frequency 0, which means that there is an instability. And okay, now you start to increase eta, and what you see when you go from 0 to 0.1, you see it moves, the leading eigenvalue moves to this location. So it moves with a certain positive frequency, which means it goes to the right against the horizontal temperature gradient. And but its growth rate reduces. Now, if you move it to even higher value of eta 0.2, so then you find that the frequency or the phase speed became even larger, but then the growth rate, it's almost 0, or maybe it's 0. Just at 0, it's just neutral perturbation place. If you increase eta even more to 0.3, well, the frequency reduces, but the growth rate also becomes negative, which means there is a stabilization of this system, of this buoyancy instability, driven by the induced vertical temperature gradient, and stabilized somehow with this eta. Okay, now if we want to look how neutral curves for the Rayleigh number as a function of the wave number look like for a given parameter set, so then you see the blue line is for eta equals 0, which means only vertical temperature gradient is present. It has a minimum at about Kc, the critical wave number, at about 0.1, which means the instability is quite long wave, I would say. And as you raise eta, as you increase the value of the horizontal temperature gradient, you see a steady rise of the neutral curves, which means actually that you stabilize the system, because the critical Rayleigh number, which corresponds to the minimum of each curve, increases with eta. Now it's a long wave instability, as I said. So Kc is a critical wave number, is very small for non-zero Biot number. Now, if the Biot number will be strictly 0, so then the minimum of this curve will be exactly at k equal to 0, which is really long wave instability. Now, in the case of eta equal to 0 and small Biot number of the critical Rayleigh number, it's about 320. If the Biot number is exactly 0, so then this is an exact value of the critical Rayleigh number. Okay, so so what happens is that so the question is why we see this stabilization, and the reason is, as I already mentioned, there is an induced VTG, and this induced vertical temperature gradient opposes the imposed temperature gradient, and it may hinder the instability, or it may even kill it, as we can see, especially now. So if I want to see how the variation of the critical Rayleigh number looks with eta for the case of small Biot number, it turns out that there is an instability island shown here by the red curve. So there is so the instability is present only here, only within this island or peninsula, whatever you want to call it. Okay, the system is stable here, it's stable here above, but it's unstable only inside. Okay, so and of course, if you go this way for a given eta, if you increase Rayleigh number, so this is a borderline of, it's actually instability threshold, but if you increase the Rayleigh number even more, so you hit the stabilization boundary, and further increase of the Rayleigh number will stabilize the system exactly by this mechanism which I just mentioned. By you increase the induced VTG and it kills the instability. You may think about the following, that maybe the way to kill the instability is just if your average temperature gradient across the layer may be zero. So then this may be a borderline between the instability and stability, and this temperature, the average temperature gradient is the zero value for this gives rise to this line, which is given by 320 divided by eta square line. And for very small Biot numbers, indeed, all these islands which move a little bit up with an increase of Prandtl number, they are all below this sort of asymptotic line. Now, one thing to remember here, that if in this case, so if the Prandtl number is larger than 1, the system is absolutely stable toward with respect to normal perturbations. To the right of this turning point, in this case, it's 0.25 or something like this. Okay. So, okay. Now, but this conjecture doesn't work well, because if you raise the Biot number from the very small value 10 to minus 5 to a medium to sort of moderately small value of 0.1, then you see that the critical curve actually crosses this asymptotic line, which now became grid instead of blue on the previous slide, which means actually that to have an instability, you don't need necessarily to have the average temperature gradient to be zero or to be negative. You may still provoke instability even in the case of the average temperature gradient becomes positive. Somewhere it's still negative, and this would be sufficient to incite instability of this kind. Now, what is interesting, that for larger value of the Biot number, like here of 0.1, still small, but sufficiently large with respect to the previously small value, the instability becomes finite wavelength, and its critical value of the wave number is about 1. Okay, now in the case of Prandtl number being smaller than 1, which is primarily liquid metals, the situation seems to be very different. Why? Because okay, if you look at this graph, which combines actually the values of the critical Rayleigh number, which are in blue, and the values of the critical wave number, which are in red. So if you follow this line, well, for sufficiently small values of this eta, well, you go more or less along the path, which we already saw in the previous slides for Prandtl number larger than 1. But then suddenly, and by the way, the instability was long wave, it was a very, very small critical wave number. Okay, then suddenly somewhere here at about 0.15, there is a dramatic turn in this line. So it goes very dramatically up, then it reaches some maximal point and then starts to decrease as more or less proportional to 1 over eta. And the critical wave number also goes up and then relaxes with an increase in eta to some finite value, in this case 0.9 or something like this. And this line, it continues forever. So which means that for the Prandtl number smaller than 1, we don't have just this instability island, but it may be, the layer may be unstable either to long wave instability in this range for sufficiently small values of eta, or to finite wavelength instability, which we call a new mode of instability in this case, which is a finite wavelength. And it continues forever with a further increase of in this eta. Maybe not related, but still related. In our previous paper, last year, we considered a pure Marangoni instability in a very similar physical setting. So then you may see, without going into detail, this is a critical Marangoni number and this is eta. So there is always an instability island, but then there is a new wave, mode of instability, which is finite mode of instability, and it exists all the time. So which means that if you have a Prandtl number larger than 0 and sufficiently thick layer, so you kill by the horizontal temperature gradient, you may kill the buoyancy instability, but you cannot kill the Marangoni instability. So which means that you may observe in experiments pure Marangoni instability in a thick layer. Okay, some nice outcome of all of this. Now, in this case of
just I notify you. Okay.
Yeah, thank you very much. Yeah, thank you. So this is just how this new mode of instability is born. So it just bifurcates very smoothly out of this instability island borderline, and then it goes by itself. Okay, so let me skip this, is much less important. Okay, we may come back to this later. In any case, let me summarize the linear part and then jump to the nonlinear part. So in the presence of an oblique temperature gradient, the induced horizontal temperature gradient component, it exerts a strong stabilizing effect, acting against the imposed vertical temperature gradient. That's a stabilization we already observed and discussed. In the case of Prandtl number larger than 1, we have an instability island, and outside of this island, the system is stable. In the case of Prandtl number smaller than 1, there is a new finite wavelength mode of instability. And again, we may observe Marangoni instability in thinner but still thick layers. Let me skip this. So the paper, whoever wants to see details, the paper just appeared in JFM. It's already on the web, so just look there. Okay, so let me briefly consider a weakly nonlinear stability analysis in 2 dimensions. Actually, most of this analysis may be extended to 3 dimensions, except for nonlinear investigation of the nonlinear evolution equation which we derived. There is some peculiarity that you need to run this to very, very large times, and sometimes to solve this, it took about a week or maybe four to 5 days. So we don't even dream about extension to three-dimensional case, at least with the current situation with the computer equipment. Well, anyway, the weakly nonlinear stability analysis may be done for small values of eta and for small values of Biot number. And we use asymptotic expansions, and we find that at leading order, we recover exactly, you are familiar with this already, value. This is a critical value for the Rayleigh number for the case of eta equal to 0, 320, the leading order temperature disturbance is some unknown function at this stage, and the velocity field is also related to this yet unknown function. So for this unknown function, we find an evolution equation. It's a partial differential equation which describes the spatiotemporal dynamics of the temperature field in this case, and it's given by this equation. It's a partial differential equation, first order in time, fourth order form in space. So it has a third order derivative, second order derivative, first order. You have all this, and doing the linear analysis based on this long wave equation. So you find again the frequency, which is exactly matches very well the results of the numerical study. And there is a growth rate, which is given by the Biot number, the Rayleigh number, the increment of the Rayleigh number above its critical value. It has eta in, and it has a wave number. So what is interesting that, let me skip this, we get a very nice expression for the critical value of the Rayleigh number. If this, as it varies with eta and with Biot number, again, for small eta and for small Biot number, look the variation of the critical Rayleigh number. This is the blue line. This is exactly numerical calculations, and this is arising from this analytical analysis. So they fit actually excellently up to almost to the turning point itself. Okay, now let me skip this. Let me go to the most important thing. So we solve this equation numerically. With an initial condition, just a small disturbance on top of this F. I will remind you, this is leading order disturbance of the temperature field on top of the base state with periodic boundary conditions. So let me go maybe to the most important thing. So this is the case with several values of eta. The horizontal temperature gradient, 0.05, 0.075, 0.1. Now, for each one, since the critical value of the Rayleigh number varies with eta, so we took the values of the Rayleigh number in such a way that there is only 5% of supercriticality above this 320, above the critical value, which depends on eta 2, and see what happens. So what happens is the following. We have traveling waves. The traveling waves, these black and red and blue colors, so they correspond to these three different cases of eta. They all travel to the right. Well, it exactly fits the analysis, the results of linear stability analysis. But what is interesting to note, please take a look on this curve, for example. You may see that the leading front of this wave is less steep than the back front. Normally, when you have a propagation of a wave, okay, normally the leading front is steeper than the rear front. In this case, it goes upside down. It goes the other way around. Okay, so now the question is why is that? So again, thermal wave propagates to the right against the horizontal temperature gradient. And again, as I said, the back front is steeper than the leading front. So we want to understand why is that? Well, if we look again at the equation, no, maybe let me go to the next slide. Yeah, over here. We see only two terms in this equation which break the left-right symmetry in this equation. First one is this dispersive term, okay, which has just a third derivative and also eta in front of it. Okay, so this guy is responsible for the direction of the wave. Okay, it goes to the right as predicted. This is absolutely clear. But there is another term which breaks the left-right symmetry, and this is this guy. This multiplied by this and differentiated here. So the question is, what does this guy do? And this guy does the following thing. Let's take just these two terms, the time derivative and this guy, which is suspect now for doing this very unusual effect. So let me write this equation in this form when alpha is just a coefficient and it's a positive. Let's differentiate this equation with respect to x and define a new dependent variable phi, just the derivative of this f with respect to x. Then this equation reduces to what I wrote here. And this equation is sort of heat equation, if you will. So for phi smaller than 0, phi, let me remind you, this is the slope of this f with respect to x. So if phi is smaller than 0, which takes place along the decreasing branch of f, so this is a normal diffusion equation because this is negative. So to speak, the diffusion coefficient is negative. So it's just normal diffusion equation which wants to smear the variation, any variation in phi. So which means it decreases the variation of phi, making the decreasing branch, which is the leading front of f, more moderate. On the other hand, if phi is positive, it goes along the rising branch, which is the rear of the front of the wave. This is a backward diffusion equation because it's kind of heat equation with the wrong sign, so to speak. Okay, so this is instability in phi, and this increases the variation in phi, so making the increasing branch, which is the back front, steeper. So this is quite an unusual thing. Let me summarize just the nonlinear part and the whole thing okay, all along. So first, in the weakly nonlinear regime, the field of temperature deviation from the base state propagates as a traveling wave against the direction of the imposed temperature gradient. And the propagation speed is proportional to eta, exactly like predicted in linear theory. But it turns out that nonlinear waves propagate much, much slower than those which than the speed predicted by the linear theory. Finally, for a small non-zero Biot number, the wavelength of the traveling waves is larger than that predicted by the linear stability analysis. And that's about it. Thank you very much.
So thank you, Alex, for the very interesting and detailed talk.
Thank you.
I think we can open the stage for questions. So to the participants, just feel free to unmute your mic and ask a question, or you can write in the chat and I can report it. Now go ahead, Hendrik.
Alex,
yeah.
You said you have this third order derivative in your evolution equation, and well, usually that's corresponds to a dispersive term, but here you have first order term as well, or not?
First order in space?
In space, first order in space.
No.
Yeah, and then maybe the third order term takes the role which the first order term usually has.
Not necessarily, because you see, let me show you. Yeah, over here. So this is the guy which stems directly only from this guy. Okay, from the dispersion. So this frequency is proportional to eta, is proportional to third power of the wave number. So it's not a translation, it's dispersion. So each mode, it travels with its own phase speed.
And then
it goes to the right.
But I thought, I was thinking of, let's say, something like the KdV equation, where you have this balance between dispersion and nonlinearity.
Right.
And in that case, you have that steepening, which is also due to the usual, let's say, third order dispersion term. And I wonder whether that plays a role here. No?
No. In that case, when you have a KdV equation, actually there is a balance between the nonlinear wave term, which is quadratic, and the dispersion. So the main effect, so for larger amplitude of the wave, so the nonlinear wave term is dominant because it's quadratic in amplitude. So it travels to the right, for example, and then what happens is that it reaches the balance with the dispersive term. Why? Because the dispersive term in KdV has a positive sign here. So the propagation is to the left, and then the balance is reached. So that's why the balance is achieved shorter wavelength, so that's why it's steepening in the direction of the traveling.
And do you say, well, here you cannot reach a balance between the nonlinearity and the...
No, there is a balance. There is a balance.
Okay.
But there is no wave term, no nonlinear wave term here. You see, the travel is invoked by the dispersion and by this guy, which is this. It's a derivative of a first derivative squared.
Okay, interesting.
Yeah, it's kind of unusual. When we first found it, I said, well, something is not logical. Yeah, but then I said, well, because there is no nonlinear wave term, so everything can happen.
Okay, thank you.
Of course, this guy is negative.
Yes.
Okay.
Yeah.
Thanks.
Sure.
Any other question? Just feel free to unmute your mic and ask a question, or just write in the chat if you have any.
Yeah, you may ask. I don't bite. Well, at least not through the computer.
Okay, maybe I can ask a couple of questions myself.
Sure, absolutely. For the same price.
So you were discussing like the nonlinear part. Afterwards, you were showing the properties of the nonlinear term depending on phi, on the sign of phi.
Yeah, over here.
Yeah, yes, exactly. So do you have any other term which is like work there you say, of course, if phi is greater than 0, then you get an instability of phi, and of course, I mean, if the coefficient of the diffusion term is negative. Okay. Do you have any other second order term with a negative coefficient, or high or even order derivation with a negative coefficient in the original?
Sure. Yeah, sure. The second derivative, for example, if you look at this guy, this is dx of this constant times the first derivative, which is essentially this multiplied by the second derivative. So it's linear second order term. And this is actually this is where the instability comes from.
Yeah.
Because if this guy is positive, so then you have an instability. So the Rayleigh number must be larger than this value multiplied by this guy. But then you have to overcome this effect of the Biot number, because if you look here, sorry for the deviation. Okay, so the neutral curve looks like this.
Mm-hmm.
This is a curve for omega I as a function of k. So it starts underneath 0 at minus Biot number value. Then it goes up because of this term which we just discussed, the Rayleigh 2 divided by 320 minus 7 multiplied by eta square. So it goes up, but then it goes down because of the fourth derivative.
Yes.
Okay. So to have an instability, you have to cross this value. Okay. So that's why this term appears there. This one. Okay. But this term, it makes its only effect is to excite instability or not. It does not break the parity between left and right.
Yes.
So, yeah. So the only suspects with respect to breaking of symmetry, there are only two terms. This guy, the dispersive term, and this one.
Yes. No, I totally agree that that the break of symmetry must come from like a term, kind of an odd term in derivatives. I was just like thinking what could be the effect of the higher order even derivatives or kind of symmetric terms. Also, like the 1/6 second order derivative in x of f, the last term in
this one wait, let me, this term it's a second derivative of the first derivative squared. Okay, this one, I think it participates in all these deformations of the pattern, but I can precisely tell you what this guy does. It's a cubic term, okay, and this term is negative.
Yes.
And this guy belongs, see what happens, you have this derivative in front of it. So this is sort of part, if you will, of the diffusion coefficient, which begins here. For small f, this one is negligible. So this is to be unstable or not to be. But this one, it's a negative addition to sort of diffusion coefficient, which means that once the pattern becomes large, in some sense,
it saturates.
Yeah, so this guy will saturate, and that's exactly what happens. So they all saturate. And the amplitude of the pattern is larger for larger value of eta. Okay. For example, for eta equal to 0.1, it's this one is 0.75, and this one is 0.05. Okay, so that guy imposes a strong upper bound on the growth of the pattern. What precisely the other guy does, this one, I don't know. It's a quadratic term. It's independent of, it does some deformation of the pattern.
And I also had another question. Maybe I can ask it straight away without. So so far, as far as I understood, I mean, you're considering cases in which basically there is like a free stress at the top. Eventually, when you include Marangoni force, okay, that's a different story. So in that case, in the case in which you will consider surface tension, that will enter in your nonlinear equation, right? Because if you consider deformations, of course, if you consider deformations of your film, then surface tension, if you consider a flat film, will tend to kind of add on this saturation term, right? Because it's gonna go flat, but
well, it will definitely add. We are doing this now for a pure Marangoni case. There are some little obstacles which I believe that we'll overcome soon. But the point is that surface, if you neglect deformation and you assume only non-deformable surface, so Marangoni will come through the variation of the surface tension there because of disturbances in the temperature field. So the problem is that the Marangoni term will appear certainly in several locations. First, it will appear somewhere here too, because it will also add to instability. So it will appear definitely here. Okay, and it will certainly appear in some nonlinear terms. Now, apparently, as far as I recall, from what I've done many years ago, if you consider only the vertical temperature gradient, you have this guy will appear with a different coefficient, but it will appear. But there will be different nonlinear term, different from what you have here. That's what I remember what I did a very long time ago. Actually, I was not the first one who did that. There was a paper by Sivashinsky going back in 1982, I think. He did this the first. So there was a different nonlinearity there. But here probably there will be a combination of all the three. So we'll see how it goes. That's what we are doing now. But, you know, just to come back to the point you made now, you mentioned, and I wanted to comment on that. So as I said in the beginning, we had to assume that the interface is non-deformable. Why? You see, there is a long-standing controversy. It's actually not a controversy, but it's almost a done deal about the effect of non-deformability on Rayleigh or buoyancy instability. So what happens, we use here the Boussinesq approximation. Now, of course, the Boussinesq approximation is an approximation. It's valid only if this product of alpha delta t is much smaller than 1, but it has also other obstacles. One of them is deformability of the interface. It turned out some few decades ago that if you combine Boussinesq approximation with deformability of the interface, you may run into some spurious effects. And this was shown. There is a review article in Applied Mechanics Reviews or something like this. I think that's the name of this, Applied Mechanic Reviews, in the year 2000 or 2001, written by Manuel Velarde and Alex Nepomniachtchi and Marcel Hennenberg of blessed memory from Brussels. So there is a chapter about that. It's called non-Boussinesqian effect, and non-deformability is one of them. So you may be very, very cautious in combining them. However, just a few months ago, one of my colleagues did, hardcore numerical simulations for many, many cases of Rayleigh instability, of buoyancy instability, where he also assumed non-deformability and deformability as I say, running in parallel and watching the critical values of the Rayleigh number and the critical value of the wavelength of the wave number when instability was was reached. And to his great surprise, in some 15 cases, different cases of different liquids, different properties he ran, only 2 or 3 had a significant difference between the 2 cases, the non-deformable and deformable. So he asked my opinion. He sent me a preprint. I read it carefully, and I said, well, I mean, if your computations show this, so that's probably life. Okay, so send it to a journal. So he submitted this paper to, I think, to Physical Review Fluids, and he's still waiting for reviews. But so now I'm even more confused, because in the past there were several papers showing explicitly that including deformability with Buoyancy approximation leads to very, very serious differences. On the other hand, these new numerical computations show the difference. So I don't know yet. So I have to sort of crystallize my own opinion about that. So if this is the case, and in most cases there is no big difference between the two, so definitely it would be a great opportunity to use Buoyancy approximation along with deformability, but again, keeping in mind that in the past there were also some glitches about that, so one should be careful about that. So that's
okay.
So that's why we chose to use a non-deformable surface, just to avoid any kind of complication.
Okay. Thanks a lot. I mean, that was
sure, absolutely, my pleasure.
And so let's see if there is someone else who would like to ask a question. So once again, just feel free to unmute your mic if you want to ask a question, or write in the chat. Okay, that doesn't. Go ahead, Henry.
No, I just I thought the remark regarding the deformability, yeah, that's interesting that that the numerics show that probably that's not in fact in practice not really a problem in most cases.
Yeah.
But as you said, one should be careful. I was aware of this warning.
Sure.
And I was really also looking, hey, where was that really probed, or who has written this up? So your hint to this review article, I will check.
Oh, well, first Alex Nepomniachtchi found this in the middle of 80s, I think. There was a paper pointing to that other paper, which appeared some 5 or 6 years before that. So those guys, they found some long wave instability with certain properties when they considered buoyancy instability for a deformable surface case. So what Alex showed that if you do it not with the Buoyancy approximation, but rather doing much more complicated, of course, analysis based on Navier-Stokes equations, and taking into consideration, because the continuity, so your liquid is not of constant density anymore. So then your continuity equation is broken up into 2 pieces. One is capital D rho by capital DT equal to 0, and the other one is just divergence of V equal to 0. But then you have 5 equations, and you need to assume something. So if you assume some relation between pressure and the temperature and the density, probably, so your analysis becomes quite intensive. And so finally he showed that in that case, they consider the instability is not long wave, it's short wave, and it has absolutely different features. And the paper was, and then they wrote this review in Applied Mechanics Reviews some 20 years ago, and it has a chapter there dedicated to these non-Boussinesque effects, and this is one of them, the deformability. Now, who did this analysis? It's Alex Gelfgard, our friend, and that's what he did, and sent a paper.
Yeah, that's right. I could imagine that he does something like that, numerics, number crunching.
Yeah. So he had, and he did this for several months, and he asked me many questions about that, and they said, okay, so it looks nice. Go ahead and do it. Well, I have a confidence in his numerical solvers and his numerical capabilities. So if these are the results he gets, so I trust him.
Okay, good, thanks.
Yeah, sure. So I hope the paper will be published soon, and we will all know whether we are able or unable to use Boussinesque approximation with deformability, which is just a key point in many cases.
That's interesting.
Sure, absolutely.
Okay.
Great.
So I think I don't see any other person who would like to ask a question. I don't see questions in the discussion. So thank you very much, Alex, for the talk. And
my pleasure. Thank you very much. Thank you very much for an invitation, and it was great to see you guys.
Yeah,
almost in real.
Yeah, it was. Also, thank you very much. It was great to see you. And I noticed once again, the key point is to find a relatively simple problem that has not yet been addressed. And I think you succeeded with this one.
Yeah, thank you very much. It's due to my postdoc. You see, sometimes, senior people just, overlook many things because they are busy with many things. Younger people, they have kind of a much sharper eyesight on what is known, what is unknown. If this is unknown, so they come in and ask, and you say, "Oh, by the way, you are right. I never saw this." And look more in literature. Then he came back. He said, "No, there is nothing about that."
Okay, you also need some luck. You need some luck to have the right hints from your guys.
Absolutely.
Yeah. Right.
Yeah. So which makes life much more interesting and much less boring.
Exactly.
This way. Yeah. Absolutely.
Okay.
Okay.
Thank you very much, Alex.
Health. Yeah, and hope to see you in person somewhere sometime soon.
Sure.
Let's hope so. All the best.
Yeah, let's hope so. Absolutely.
Goodbye.
Good evening.
Bye. Good evening. Bye.
Bye.
Bye, guys.
Everybody.
Bye.